Hello students, today I will be discussed about conformational analysis of acyclic compounds part 3, and this is the last part of your syllabus. In the last lecture we have discussed about the conformational analysis of ethane, N-propane, N-butane, 2-methylbutane and 2,3 dimethylbutane. Today's lecture we started with the conformation of haloalkanes. From here we will restrict our discussion up to which one is more stable and why, and which one is less stable and why. First of all, today's first compound is start from haloalkanes. Will be discussed about up to 2 carbons, 1, 2, 3 or 4 carbons. So conformational analysis of haloalkanes. First, I take an example of here, that is 1-chloropropane. Now, if I consider the rotation among the 1 and 2, that is C1 and C2, then we will got such kind of conformations. Look at this. This one is the 1, 2. That is 1, 2, 3. So take this as a methyl group. So 1, 2, 3 is this one, and if we consider the rotation of this one, so clearly this one is the most stable conformation. Chlorine, methyl, and the rest of the hydrogen. So this one is this. Is clearly this one is plus minus AP, or we will call this as a NT. And this one is less stable. I will discuss why it is less stable. Now, if I consider another conformation which will looks like this one, that is this, so it will fit with this one. Is chlorine and methyl is here, so they are gauge to each other. So they are gauge to each other. That means this will be positive 60 degree. Hence, we call this G plus, or you may tell it is a positive or P isomer. Similarly, if we take this its mirror image, that will be this one is called the minus M or G minus isomer is here. And these are the more stable than this one. So in equilibrium, all three are present there, but the eclipse form is considerably less present because there will be some interaction between the unstable interaction between them. That's why eclipse conformation is not considered here. So why this gauge conformation are more stable? This is due to the London force. This is nothing but when van der Waals force is attractive in nature. So these are the attract to each other. This type of force is called the attractive force, and it's specially termed as London force. As they are in 60 degree angle, so their restriction, that is steric interaction, is minimum but lesser than that of the eclipse conformation, but it has some attractive interaction between them. This is the stabilizing force for this gauge conformation, and these are separated by a distance only 60 to 70 degrees centigrade, and their sum of their van der Waals radius apart from their sum of their van der Waals radius. So the repulsive force are less. But in these cases, there is such kind of attractive force or seize or not present here. That's why this will be relatively less stable than this one, as there is a attractive force which is stabilized in nature is present here. So this is our first conformation. Next, I move to our second part, that is haloalkane. Now, if we replace this by another chlorine atom, so it will gives the 1, 2 dichloroethane, or you may take this bromine as also. So now my next example is, this one is this one. That may be the Cl, or these two may be, okay. So Cl or both gives the same kind of result. Here the possible conformations are, of course eclipse will be there, so you can write the eclipse conformation here, so that's not important here. But now we can draw, this one is X and that one is also X. If we consider this as a X, if we consider this as a X, then there will be X. So this is the gauge conformation of this one. And if this one is another X and this will be another x. So this will be anti-conformation, and it will be clearly x, and this will also be x. So here the dipolar interaction. This acts as a dipole, and here is also a dipole is present there. In the same cases will be there is a dipole interaction, dipole repulsive interaction will be present, and this makes it what stable? This make it less stable. Gauge form is less stable here. So this one will be the less stable here due to the dipole interaction. What? Dipole interaction of 2 chlorine or 2 bromine present in the gauge form. Since both of them have finite value, the dipole moments are not zero. I come to later. Here this one is anti-conformation, and this one will be more stable, as the destabilizing force is equals to, destabilizing force is not present there. The dipole interaction is not present. They are apart from each other. That will be 180 degree and apart from each other. So this repulsive interaction is absent. Now, in the equilibrium, overall equilibrium has some positive dipole moment. Now, if this one is 100% in the equilibrium, then its dipole moment, its dipole moment should be 0. That's mean equals to 0. The dipoles are cancelled to each other. That's why they should be 0. But it has a considerable dipole moment. So, this has some contribution towards its equilibrium, but here the anti-form is more stable than the gauge form. Okay. Now the amount of gauge conformation will be increases in presence of polar solvent, so that this kind of dipolar interaction will be lesser in polar solvent. So this will be dependent on the solvent. If we increase the solvent polarity, the amount of gauge conformations in the equilibrium will be increased. Okay. So now come to the example 3. Example 3 is the another beautiful example. Now if I take this as a fluorine, okay, if I take this as a fluorine, so it is somewhat different explanation, because I let this one is fluorine here and this one will be the fluorine here. Of course this will be the anti-form, and if this one we treat this as the gauge form, okay, this one is treat this as gauge form. Treat this as gauge form. Now in equilibrium, this will be in higher amount and this will be this. So clearly this one is less stable. Okay. Again, its anti-conformation is less stable, but its gauge conformation is more stable. Now the question is somewhat different explanation will be given. Why somewhat different explanation will be given here? Because fluorine has smaller in size and having higher electronegativity than chlorine or the bromine present there. So it can be explained on the basis of hyperconjugative interactive force. So we have to be write down the hyperconjugation possible for this compound, that is FCH2F. So such kind of hyperconjugation may possible here. CH2, CH, F, and the proton is here. So in these cases, hyperconjugation may possibly just like this goes to here and goes to there. So it will be fluorine is minus. Now it's no bond, CH2 double bond CHF, and the hydrogen plus is here. So this one is this, and another is possible if this fluorine is involved here. Then in that case it will be, this will be CH. I think this will be CH2F. Let's okay, CH2F because hydrogen. So now in these cases it will be CHF H plus. That is another compound. Double bond CH2 and the F minus. So there is no bond between them. Some no bond should be there. So these are the possible hyperconjugation are possible. Now to involve, in order to involve both the fluorine atom in the hyperconjugation, we need such kind of structure in it. That means gauge form, when the 1,2 difluoroethane present in the gauge form, it's both the fluorine will be involved in the hyperconjugation. That means it will be more stable. So due to such kind of hyperconjugation, when the both simultaneous fluorine atoms are involved in this kind of hyperconjugation, it will be more stable. That is the first explanation. Second explanation is this one. Small size of fluorine atom minimizes the van der Waals repulsive interaction in the gauge conformal because they are smaller in size, so the dipole repulsion, that is also van der Waals repulsion, will be lower here. That means we got the lesser destabilizing force, and fluorine is higher electronegative atom. It has highest electronegativity, so it shows the gauge effect because the lone pair are present there, so they can prefer to occupy the gauge position to each other. So this is the explanation why the gauge form for 1,2 difluoroethane are more stable. So this is all about our 1,2 dihaloethane. So now we move to the compounds. If this one is increases here, that is CH3, CH2, CH2Cl, you may consult your book so that you can explain this one, how this one is more preferable. So this you may treat this as housework or your homework. Now I move to the next part of the conformational analysis, that is the compound which can forms the hydrogen bond. Okay, so compounds which can forms the hydrogen bonding. So first of all is 1,2 diol. Yes, 1,2 diol can forms the hydrogen bond, and how? So this will be my next part is this one, that is the conformation of containing the hydrogen bond. So conformation of some hydrogen bonded acyclic. Okay, so this is right. So first of all, we take the example of this one, that is CH2, CH2, OH and OH. So this is the first example, that is 1,2 diol, which we may treat as this as a ethylene glycol. We may treat this as a ethylene glycol. So what are the possible conformation? So write this as this one. So this one will be the OH, and this one is H, and rest of these are hydrogen. So this clearly this one will be the G plus form or the gauge form of the corresponding this one. Now if we take the minus form, so in this case this will be again looks like this: hydrogen, 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 hydrogen. So this one is G minus. This one will be empty form is here. The empty form OH, hydrogen, 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 and hydrogen. So clearly this one is the empty. Now, so there is no hydrogen bonding is possible in case of empty, but in this case such kind of hydrogen bonding may possible. So it is a stabilizing energy. So it gives the stability to the gauge conformation. So hydrogen bonding is possible only when the angle between these two groups is 60 to 70 degree, and the van der Waals repulsion interaction are very strong and act as a destabilizing factor, but the hydrogen bonding will now act as the stabilizing force. The gauge conformation is torsion angle, what, that is 60 to 70 or minus 60 to minus 70, two interacting groups are conformationally suitable to forms the corresponding hydrogen bonding and make it the more stable here. So now if we generalize this compound, in the antiphor there is no such kind of hydrogen bonding is possible. But hydrogen bonding is possible in case of, look at this one, hydrogen bonding is possible in case of the eclipsed conformation, that is the CH2OH. So hydrogen bonding is possible here, but there will be some steric hindrance operated between these two oxygen and this bond. That's why such kind of hydrogen bonding are possible by this way. So look at this hydrogen oxygen, and it will make this here. So that is the actual position to make the hydrogen bonding more favorable here. Okay, so this is again for the minus M isomer, but in case of the anti-conformation there will be no such kind of hydrogen bonding is possible. Okay, no such kind of hydrogen bonding is possible between these two, maximum distance was there. So now if we generalize this compound, if we make this and we replace this with another atom that is called X. Okay, so another atom and make it as X. So if we replace this with the X, so what should happen here? Now X may be possible, X may be equal to X, here X may be equals to another chlorine or NO2, okay, or NO2 or fluorine, NHR, NR2, NHR, NR2, etc. So look at this, all can form the bond, but in our syllabus we will confirm with this one, this is the halohydrin. Halohydrin will be included in the syllabus. Now, if we make this now X, simply it will be converted to X. So the hydrogen will be now bonded just like this, and in this case as now it will be moved to the X here. Okay, so it will be now converted to the X, that is the rear carbon atom replaced by the X here. So that is the general structure for the compounds of just like this. So this can form the hydrogen bonding. This hydrogen can form the hydrogen bonding with this one. So this made the halohydrin. I will come to the later. Now, if I take another example, that is the one of the hydrogen is replaced by the CH3. Okay, one of the hydrogen is replaced by CH3 and make it OH. So what is the name of this compound? This is named as 1, 2, 3 and 4. So it will be 2,4 diol. Yes or no? It will be 2,4 diol. So if I take the model of 2,4 diol, so look at this one, 1, 2, 3, 4, and these are the two OH group. Hydrogen is not shown here. So it may be the meso, yes or no? This may be the meso, or it may be the plus or minus, that is in DL pair, it may be plus or minus, its mirror image will be, if it is D, then its mirror image will be there. So this will be the active conformation. First of all, we have to go to the meso conformation. So what will be the hydrogen bonding possible for this meso compound? Now if we want to draw the hydrogen bonding of this one, so it will be looks like this, yes or no? So the hydrogen bonding will be formed by this, and the compound will be converted to the OH is here. But the CH3 that will be front carbon CH3 will be this one, and this CH3 will be here, and both of this will be hydrogen. So this is now Gauch or other. So this is the hydrogen bonding possible. But these two methyl groups are in what? These two methyl groups are in Gauch conformation, so there will be destabilizing force will be present. Now, if I take the if we take the plus or minus isomer, then what will be its hydrogen bonding conformation? So, what conformation forms the hydrogen bonding? If we take this one, that is the front carbon is here, and it will be goes to there. That is 1, 2, 3, 4. OH can form this hydrogen bonding. So by this one, okay. So that is the conformation, or we may looks like this, or we may hold it just like this. So it will now move to this. Yes or no? So this will now this will now move to the what? This will now move to the CH3, and this will also another CH3, and this is one of the hydrogen, and that is another of the OH group. So these are the two OH groups for the active conformation. So this one is for the meso compound, and this one is plus or minus. That is the active conformation. How it can forms the corresponding hydrogen. So it can form the hydrogen bond by this way, and hydrogen will be here. So this is the conformation by which it can form the hydrogen bond. Look at the position of this methyl group. Look at the position of this methyl group. So in this case, this goes to here. So which hydrogen bonded form is more stable? Clearly, this one is more stable. So in equilibrium, this one will be the less stable. So if we discussed about the hydrogen bonded to non-bonded conformer, which one will be the higher? Here hydrogen bonded will be more with this, because this one is more stable. So its non-bonded will be lesser. So the ratio of bonded to non-bonded will be higher in this case, that is in active conformer, and lower in this case. You may ask this one, so which one has the higher bonded to non-bonded conformation? You have to be told that it has higher, but it will be lesser. So this is our compounds which can form the hydrogen bond when they are in, and these two groups are in gauge conformation. Okay, in this cases the eclipsed conformation are more stable, but again it will be destabilizing force will be there due to the steric hindrance between these groups. So now I come to the compound that is called the halohydrogen. I have already discussed this compound, that on this one, that is CH2, and this one will be the Cl here. If this one is Cl, this is called the chlorohydrin. If one is X, then this will be the halohydrin. So you can again explain by the previous general structure, that is, if these two are hydrogens, then, and this one is chlorine here. So if we replace this one is chlorine and this one is hydrogen. So this is the hydrogen bonded. This is the hydrogen bonded eclipsed conformation of halohydrogen. Clearly, this one will be the more stable or more contributing conformation towards its equilibrium. So by this way, we can explain the hydrogen bonded compound, and this last part, that is conformation of conjugated system. Okay, conjugated system. So this is the last part of this portion, that is the conjugated system. If we consider this as my example, that is CH2, okay, double bond CH, single bond CH, double bond CH2. But know this name of the compound 1, 2, 3, 4. So this will be 1, 3 butadiene. So it may be present just like this, or it may be present just like this. Clearly. So if we consider the model, if we look at this model, so this is the model of this one. Because the hydrogen will be here, and the hydrogens will be here. So this is the model for this one, that is some destabilizing force here, and the hydrogen, and hydrogen. So by this we got this one, that is this. So they are away from this one. Clearly, this one is more stable, and this one is the less stable. This one is the less stable, and this one is called cis conformation. This one is called cis conformation, and this one is called trans conformation. Clearly, so this one will be cis, and this one will be the trans conformation. there will be some steric hindrance between these two hydrogen, makes it less stable. You will be studied this conformation when you will be pericyclic reaction. The cissoid, this one is called cissoid and this one is called the transoid also. So cissoid will be more preferable there. Now if this one will be the C double bond O, so in these cases this will be C double bond O, and if this one is this one, then this will be the C double bond O. Okay, so this is the hydrogen, another hydrogen will be there. So by this way we can explain the, that is S transform will be this one, that is S transform, and this will be a cis form for the compound. It will be this one CH3, then it will be CH3, CH3 and CH3, it will be mesitile oxide. Equals to the CH3, CH3 and CH3, so it will be CH3, CH3 and CH3. Then this compound is called the mesitile oxide, is alpha beta unsaturated and alpha beta unsaturated system, the conjugated system, SCs or S trans. But the stability again, and they will be similar. Then another example, acrolein, acrylic acid, you may go through there. So this is all about your conformational analysis of the acyclic compound. So all of these are explained here by the 3 parts, that is part 1, part 2 and part 3. Hope it will be very much useful to all of you. We will meet again with another new video. Okay.